A lone spacecraft, hurtling through the silent void, more than 12 billion miles, or 20 billion kilometers, from the only home it has ever known, Earth. Launched in 1977 with a mission expected to last mere years, Voyager 2 has defied every expectation, surviving nearly 5 decades. It carries the golden record, a time capsule of humanity, music, greetings in 55 languages, images of our world, and the blueprint of life itself. This is more than a spacecraft. It is humanity's first messenger into the galaxy, a fragile envoy at the edge of forever. And now, Voyager 2's final transmission has confirmed what we all feared. This is one cosmic story you won't want to miss. Origins of the Grand Tour. In the mid-1960s, while the world's attention was largely fixed on the space race between the United States and the Soviet Union, a quiet but transformative discovery was taking shape at NASA's Jet Propulsion Laboratory, or JPL, in Pasadena, California. It was 1965, and Gary Flandreau, then a doctoral student at the California Institute of Technology working as a summer intern at JPL, made an observation that would change the trajectory of planetary exploration. Using little more than pencil calculations and ephemeris tables, he realized that the outer planets Jupiter, Saturn, Uranus, and Neptune were slowly moving into a rare alignment, an event that occurs only once every 176 years. This cosmic arrangement, he recognized, could be exploited to send a spacecraft on a grand tour of the outer solar system. Instead of expending enormous amounts of fuel to reach each planet individually, a single probe could use gravity assists, or slingshots around planets, to gain momentum and alter its path from one giant world to the next. This made the impossible suddenly plausible. At the time, NASA was consumed with the Apollo program and the ambition to land a man on the moon before the decade's end. Yet the implications of Flandreau's realization were too important to ignore. If engineers could design a probe capable of surviving a decade-long journey through deep space, it could revolutionize humankind's knowledge of the outer planets. Without the Grand Tour trajectory, such a mission would have been far too costly and time-consuming, requiring separate launches to reach each planet. With it, a single craft could achieve in 12 years what might otherwise take 30. The opportunity was fleeting. The alignment would not occur again until the 22nd century. The clock was ticking. As the 1970s approached, the vision began to take shape. Engineers at JPL and scientists across NASA started planning what was first called the Mariner Jupiter-Saturn mission, initially conceived as an ambitious expansion of the successful Mariner program. But the potential revealed by Flandreau's alignment inspired larger ambitions. Why stop at Jupiter and Saturn if the same trajectory could, with careful navigation, carry a spacecraft to Uranus and Neptune as well? The concept of the Grand Tour was formally studied, and though budget constraints forced NASA to scale down the original proposal for 4 spacecraft into just 2, the dream survived. In 1972, Congress approved funding for the Voyager program. Launched just weeks apart in the late summer of 1977, Voyager 1 and Voyager 2 were built as twin spacecraft but given slightly different missions. Voyager 1, launched on September 5, 1977, was placed on a faster trajectory to fly past Jupiter and Saturn and then head out of the ecliptic plane. Voyager 2, launched earlier on August 20, 1977, took a longer, slower path, one that would allow it to take advantage of the full planetary alignment. It was Voyager 2 that became the true embodiment of Flandreau's Grand Tour. While Voyager 1 completed its encounters with Jupiter in 1979 and Saturn in 1980, Voyager 2 continued on, bound for the uncharted territories of Uranus and Neptune. Voyager 2's passage by Jupiter in July 1979 delivered the first hint of the extraordinary science the Grand Tour would produce. It observed the planet's turbulent atmosphere in unprecedented detail, captured images of its faint ring system, and revealed the volcanic activity on its moon. At Saturn, which Voyager 2 reached in August 1981, it recorded the planet's intricate rings and discovered new moons. Yet even these discoveries were a prelude to what made Voyager 2 unique: the voyage of Voyager 2. On January 24, 1986, Voyager 2 made its closest approach to Uranus, passing within 81,500 kilometers, or 50,600 miles, of the planet's cloud tops. This was a moment of historic significance, the first and only time a spacecraft has flown by Uranus. The data shocked scientists. Uranus, long thought to be a bland and featureless ice giant, revealed a tilted magnetic field unlike anything seen before, offset from the planet's center and tilted 59 degrees from its axis of rotation. Voyager 2 also captured images of the planet's faint rings and discovered 10 previously unknown moons, dramatically expanding knowledge of the Uranian system. Even more puzzling was the planet's temperature. Voyager 2 measured Uranus's atmosphere as the coldest of any planet, plunging to -224 degrees Celsius or -371 degrees Fahrenheit. These findings appended prior assumptions. They also proved how little we knew about the ice giants. 3 years later, Voyager 2 achieved another first. On August 25, 1989, it swept past Neptune, coming within 4,950 kilometers, or 3,080 miles, of the planet's north pole. No spacecraft has visited Neptune since, making Voyager 2's data still the definitive reference for the planet. The flyby revealed Neptune as a surprisingly dynamic world, dominated by supersonic winds reaching 2,100 km per hour, or 1,300 miles per hour, and home to massive storm systems like the Great Dark Spot, a vortex nearly the size of Earth. Voyager 2 also discovered 6 new moons and confirmed the presence of faint rings. Perhaps most astonishing were its images of Triton, Neptune's largest moon, where it found geysers of nitrogen erupting into space, a sign of active processes on a world once assumed to be frozen and inert. By completing flybys of Jupiter, Saturn, Uranus, and Neptune, Voyager 2 accomplished what no other spacecraft had done, a full planetary grand tour. Without Flandreau's insight in 1965, this window of opportunity would have closed for centuries, and humanity would still be blind to the wonders of the ice giants. For a cost of about $865 million in 1977 dollars, roughly $4 billion adjusted for inflation, the 2 Voyager probes have continued to return data for nearly 5 decades. The spacecraft carried 11 scientific instruments, including imaging systems, magnetometers, plasma detectors, and cosmic ray sensors, all designed to operate autonomously across billions of kilometers. Its longevity, far surpassing its initial 5-year mission design, demonstrated the durability of 1970s engineering and the effectiveness of long-range mission planning. Each planetary flyby required precise navigation and timing, leveraging gravity assists to reach the next target. The spacecraft's instruments continued to transmit data long after the encounters. Then came the moment of truth.